Okay, hi, Assalamualaikum warahmatullahi wabarakatuh, and a good day. So, today we continue our topic on the series Disimoto, and I hope to all of you already done to do the revision about the controlling the speed of Disimoto. Okay, because we have three type, which is we have been discussed in the class, which is the by adjusting or put the additional resistance, and then the second one varying the terminal voltage, and the last one adjusting the field flux. So I hope all of you already done doing the exercise, and today we continue our topic on the series Dismoto. So if you know the connection or the schematic diagram of the series motor, is very simple. Okay, so the series winding compose a small number of turns as compared to the shunt field winding. Okay, so and then the current of the series winding is equal to the armature current. Okay, so if you can see here, so the circuit is in series compared to the previous circuit. For the shunt, we have the IA plus with the IF to get the value of the total current. So but according to this series, so the current is equal. And then the field current of the shunt machine is constant regardless of the loading condition, which is the armature current, and the series machine on the other hand has a field current varying with the loading of the motor. Example, they have a heavier load, so the stronger field. At light no load condition, the field of the series motor is very small. Okay, so this is the basic concept of the series DC motor. Okay. Okay, according to the series Disimoto, so we also must know about the flux saturation curve as shown in figure 5.0. So why they have a flux saturation curve? Okay, so according to this one, okay, the field coil is wound around the metal core. Okay, so at the stator lah. So the field coil is wound around the metal core at the stator, and then the current of the field winding produce flux inside the core. Okay, so for this point, okay, you must take note. The current of field winding produce the flux inside the core. When the current increase, so once we increase the current, the flux increases linear proportion. So once we increase the current, so the flux also will be increased proportion. But once the core is saturated, okay, once the core is saturated, the flux tends to increase at the progressively diminishing rate when the field current increase. So that's why they have a flux saturation curve. Okay, so for the series motor, they have a same basic equation used for the separately excited or shunt motor. So I want to all of you, okay, I want all of you try to derive by your own how to get all this value. Okay, so according this one, because they have some quite different, because the value for this value is a series. So so the value of current is same. So I want all of you doing this exercise, okay, how to derive to get the final value of the speed. I want all of you find the speed equation. So maybe you have some quite different, but the I want all of you know the step by step to get this equation, because the equation of the speed is quite different compared to the other type series, as I mentioned before. Okay, so please, I want all of you take note for this one, how to uh, how to uh, derive the equation for the series motor. Okay, So for the series part, there have some different, okay, compared to the other type of DC motor, because here I want to all of you looking at the flux versus the IF graph. Okay, so assume the motor operate in a linear region of the saturation curve, that is, flux is equal to C time with the IA. Okay, for the equation 5.19, where the C is a constant. Okay, C is a proportionality constant. The developed torque in this case can be represented by, so if you know, the torque developed is equal to the kV IA. So if you replace the equation of V is equal to C times with the IA, so you can get the torque developed is equal to the K times with the C, which is the constant, IA square, to get the value 5.20. So I want all of you try to jot down this equation at your blank paper. And then and then you try to substituting the equation 5.19 and 2.0 into the equation 5.18, and then you can get this value. Okay, so just replace the value. So I want all of you I want all of you try to do this equation to get this equation, which is the speed is equal to Vt over KCIA minus with the IA plus RF over KC, to get the final equation for the 5.21. Okay. For the equation 5.1 can also obtain as a function of the developed torque. Okay, because the value of IA is equal to square torque developed to the KC. Okay, so you just replace, okay, the value of IA to get the equation 5.22. Okay, please do by your own. Okay. Okay, according to this equation, okay, equation 5.21 and 5.22 show that the speed at no load or light load is excessively high. So once the motor is no load, so what happened to the rotor? So the rotor is very high speed and maybe damaging due to the excessive centrifugal force exerted to the rotor. So for this reason, that's why the series motor must always be connected to the mechanical load. Because why we need always connected to the mechanical load? Because once the series DC motor is no load, the speed is very high. So this is the reason why the series motor must be always connected to the mechanical load. Okay, based on the previous slide, the series motor must be always connected to the mechanical load. So I want all of you imagine why, how, what happened. Okay, sorry. What happened for the series DC motor is losses their load. So what happened? So if you read for the second sentence, okay, the load could be lost when the shaft break or if a drive pin is short. So when this occurred, okay, so once this occurred, okay, you can see for this graph, okay, the current will fall to the minimum, okay, to the minimum. So what happened once the current, okay, fall to the minimum? So the motor speed will be increased. So according this one, so once the current is fall into very minimum, so the motor will move very fast and fast. Okay, because if you remember, once I said before, Okay, so once the series motor at the no load condition, the motor is very fast. So what happen once the load is broken, of the drive pin is shut, so the motor will move very fast. So that's why, um, if you see this sentence, okay, the condition is called a runway. So according this one, when the winding are pulled loose, they will catch on the field winding pole piece, and the motor will severely damage. Okay, so this condition we call runaway. So if you can see why a DC motor must have a type runaway protection. Okay, so they have two types, okay, which is you can connect the switch connected to the motor to de-energize the motor starter coil if the RPM exceeds the set amount. Other sensor can be used, okay, to energize the circuit if the motor current drop while full voltage is applied to the motor. So you can see the relationship. So what happened if the if this condition happen, so what happen? Okay, the current will drop to the minimum and the motor will move very fast. And then what happen to your motor? So your motor will be damaged. So this condition we call as a runaway, and then we need to install the runaway protection. So for the first, I repeat again, to the first thing, switch can be connected to the motor, and then to energize the motor starter coil if the RPM exceed a set amount. And then another one, sensors can be used to energize the circuit if the motor current drop while full voltage is applied to the motor. So I hope I want to all of you understand the basic thing of the series DC motor in terms of this protection. Okay, I hope all of you still remember the speed and torque characteristic, and this is the speed torque characteristic for the series motor. So this characteristic is come out from this equation for the 5.22. So what happened if any condition in the final exam question or test question, okay, it must be related to this equation. So you must know how to derive this question, and then what is the relationship. So according to this one, so what happened? So you must note that the speed of the motor is rapidly decreased when the load torque increase. So it is inversely proportional, okay, condition for speed torque characteristic. Okay, so I want all of you still remember what happened any condition if in the final exam, uh, any value. So if you want to need, if the question need you explain, so you must have the capability to explain this characteristic. Okay, the starting current of a series motor, the speed is set to the zero. Okay, so the E is equal to zero. So what happened to the starting current? So the starting current is equal to Vt divided by Ra plus Rf for the like the equation 5.23. So according this equation, okay, compare equation 5.23 to the of the separately or shunt DC motor. Okay, so you need to compare. Note that for the same terminal voltage, the starting current of the series motor is smaller than the starting current of shunt due to the presence of RF equation. Okay, so you can compare the starting current for the separately and shunt DC motor compared to the series DC motor. So that's why you must strong in the basic to derive the equation from the circuit. Okay, I repeat again, you must strong on derivation of the circuit. Okay, so we move for the next slide. Okay, if we ignore the core saturation, the starting torque of the series motor is equal to, okay, so the starting torque is equal to the kV starting current is equal to the kc starting current square, and then just replace to the value of the starting current is equal to kc Vt over Ra plus Rf square to produce the equation 5.24. So I want all of you jot down this equation. Okay, recall the starting current of the torque of shunt DC motor. T shunt is equal to Kp Vt over Ra, and then rewrite the starting torque shunt equation with the assumption, okay, assumption that the flux is proportional to the field current. So the starting torque starting for the shunt, which is the Kv times with the Vt over Ra, and then just replacing the phi with the C, and then the equal to the Kc Vt over the Rf shunt, Vt-Ra is equal to Kc Vt square over Ra Rf shunt, where the Rf shunt is the resistance of the field winding. So this will produce the equation 5.25. Okay, so according to this one, okay, so you can see here what is the different the starting torque for the series and shunt. Okay, so this has some different. So I want all of you try to make the separate table. Okay, separate table for the series, shunt, separate excited, and you can see what is the comparison, the difference of the equation. Okay, so this is just you just can take note that, okay, that the shunt, if the field resistance of the shunt this motor is usually a few hundred times higher than the field resistance Rf of the DC motor, and if we assume the Kc is equation 1 and 2 are comparable value, one can conclude that the starting torque of the series motor is much larger than the series larger than for the shunt motor. Also keep in mind that the starting current of the series motor is lower than the shunt motor. Okay, so you can try relate with the equation. Okay, another great features for the series motor is the ability to be directly driven by the AC supply. Okay, to explain this, let us examine the circuit of the series DC motor when the source voltage reverse is the proportional is follows. So since the field and armature inductance of the series motor are small, EA reverse its polarity without any tangible delay. Hence, EA is always in a phase with the supply voltage, and field current is also in a phase with the supply voltage. So since the value of speed EA is over kV, the speed of the motor is remain unchanged when the both EA and phi reverse their polarities. Okay, so because of this important feature, we can find DC series motor use household appliance and tools such as blender, food processor, washing machine, drills, circular saw. Okay, so you can try to get what is the you find out, okay, what is the application that suit with the series DC motor, the shunt DC motor, and separately excited DC motor. So so you will understand why the DC motor can why the series motor can connect it to the AC and etc. Okay. Okay, so how to control the speed of the series motor. So you must know the final equation of the speed DC motor, or the equation for the uh, final equation for the speed series DC motor, which is the Vt is equal to Vt over Kv minus with the Ra plus Rf over Kv square times with the TD, which is the torque developed, that the equation for 6.27. So this is in the DC motor they have a lot of equation. So but if you strong in the basic, so I think you are very solid to facing the final exam, okay, or test. Okay, after examining the speed torque equation, the series motor equation 6.27, one can conclude that there are three methods to control speed of the series DC motor. Okay, so for the first, same goes another type of DC motor. Okay, for the first, by adding the resistance in the armature circuit, and then adjusting the armature voltage and adjusting the field current. Okay, for the first, controlling the speed by adding the resistor to the armature circuit. Okay, so you can see here, okay, for the equation 6.28, okay, torque developed is equal to the KVIA equal to the KCI square. Okay, the flood equation 6.28 is assumed to be linearly proportional to the armature current. Again, and then the equation 6.28 shows that for the given load torque, the armature current of the motor is a constant. Okay, the change in the armature current is only proportional to the change in the load torque. Okay, by assuming that the phi is equal to the CIA, the equation 6.27 can be approximated as, okay, so this equation same, okay, the same with the other type of DC motor, but only they have maybe the Ra plus Rf and etc. But to get the value of speed, the initial speed at the no load speed minus with the speed drop of the motor. So the equation will be like as a equation 6.29. Okay, so by controlling the speed by adding the resistor to the armature circuit, if the resistance R additional is inserted in the series with the armature circuit, equation 6.9 can be modified like this one. So Ra plus the Rf and the R additional. So according to this one, so your circuit will be like this one. So they have same goes to the other type, like a separate excited shunt. The additional resistor will be here. Okay, so if we assume that the load torque is unchanged, then the armature current is a constant. In the addition, if the supply voltage is unchanged, then the motor speed is reduced when the resistance is added to the armature circuit. Okay, so this is due to the uh, increase in the speed drop. Okay, so I think all of you is clear for this one, because very simple. Just add the value of the resistors, and then you can see what happened to the speed drop. Okay. Okay, so for the next, by controlling speed by adjusting the armature voltage. Okay, so what happened, the change is the change in the armature voltage has a similar effect on the series motor as a insertion of an armature resistance. Okay, for a constant torque, the motor current is a constant, and the first term, no load speed in the equation 6.29, okay, decrease with the decreasing the voltage, and then the second term of the speed drop remained unchanged. Okay, the result is a decrease in the motor speed. Okay, so since the voltage must be kept at the or below the rated value, this type control is suitable for speed reduction below the rated speed. So this one is very clear. Okay, so what happened if you adjusting the armature voltage? So you can see what happened to the speed and what happened to the speed drop. Okay. Okay, and then the last one, controlling the speed by adjusting the field current. Okay, so how we want to adjusting the field current. Okay, so if a resistance RF additional is inserted in the shunt with the series field winding, the field current is reduced by following this equation. So you add the RF additional here to control, to adjusting the field current. Okay, so if you want to adjust the field current, you must add the field resistance additional here. Okay, so you put in a parallel. Okay, you in this term insert a shunt. Okay, but actually shunt is a parallel. Okay, if the field flux is assumed to be proportional to the field current, okay, V is equal to CIF, then the KV is equal to KCA RIE. Okay, so also the load torque equation become to be like this. Okay, 6.33. Okay, so maybe once you have maybe once you doing the exercise, so you must get what is the effect by controlling this condition. Okay, so according to this one, modify the equation 6.37 to include the newly added resistance. Okay, so I want all of you try, this equation 6.34, and then you try to get the equation 6.35. So please take note for this one to make sure you understand how to get this value and etc. Okay, so controlling the speed by adjusting field current, reduction of the RF addition result is current reduction of the field winding, which lead to the increase of the speed motor. So what happened? So if you can see here, this value, the RF additional is more higher than the RF additional 2, and then more higher to the RF additional 3. Okay, this type of the speed control must be performed with the care. So the the current of the motor is not excessive. This can be seen by examining the equation 6.3. If the torque is assumed to the constant, the armature current will increase if the RF additional is reduced. So please once again, please try doing by yourself to understand the relationship of the equation. Okay, so I want all of you try for example A. Okay, because here is you can they have some solution here. Okay, they have a solution you can follow to get this value, for example A, and then again try